So let's do an example, okay? How much energy is required to excite hydrogen from its ground state to the n is equal to 3 level? What wavelength of light is required to make this transition in units of nanometers? So basically what we're doing is, suppose we wanted to use light not to populate all of the energy levels like I showed you in this diagram. So in one of these emission tubes, you're just putting a crap ton of energy in there, so it gives you all of the wavelengths, or it gives you all of the fingerprints from those various transitions. However, what this question is asking you, suppose I want to very specifically only use enough energy to go from level 1 to level 3. We can also do that, okay? So how much energy is required? So that's going to be our Rydberg equation. And this is how that equation is going to go. It says, man, this is bugging me that I got this box right here. Can I erase that box? No. What are you doing? Oh, brother. Jeez Louise. Okay, that's fine. We'll deal with it. Okay, so delta En, so that equals negative 2.178 times 10 to the minus 18 joules. That's the Rydberg constant. And it's times this thing over here, z squared over n squared. And then when we make this delta, it becomes z squared over delta n squared. So z squared is nuclear charge. And for hydrogen, z equals 1. It's got 1 proton, so z equals 1. So for hydrogen, what this ends up becoming is now, I'll just say, it becomes 1 over delta n squared. And the way that I do that, the way that's going to work is, that means it becomes 1 over n final squared minus 1 over n initial squared. So once you establish that's how you do it, then this calculation is actually pretty straightforward, okay? And there is a negative sign in that equation, and I'll show you what that means in a second, okay? So negative 2.178 times 10 minus 18 joules times 1 over n final squared minus 1 over n initial squared. So because it's asking us to excite, the ground state is my initial, and the excited state is my final. If this were asking us what color of light is emitted, then it would be the opposite. We'd be starting at level 3 and going down to level 1. Okay. So now that's 1 over n final, and it's just simply 1 over 3 squared. It's literally just that value of n, 3, 1 over 3 squared minus 1 over 1 squared. As simple as that. Okay. And so now, that gives us negative 2.178 by 10 minus 18 joules. And that's going to be it's going to be times 1 over 9 minus 1. Okay? So first what I'm going to do is just say 1 divided by 9 equals, and then minus 1 equals. And so now that gives me negative 2.178 times 10 to the minus 18 joules times negative 0.888 repeating. And I'm just going to leave that in the calculator. And now I'm going to say times 2.178 E18 negative. And then I forgot to put the negative sign on my calculator, but I recognize a negative times a negative is going to give me a positive. So that's positive 1.936. And I can use 4 sig figs here because I have 4 sig figs from the Rydberg. So times 10 minus 18 joules. So now what's the significance of the sign? Well, the fact that this had a positive sign tells me I have to put energy in, which makes sense because that's exactly what I'm showing on my diagram. Positive energy goes in. If it were the other way, right, if I had flipped this, so if it was going from level 3 to level 1, I would get the same value, but it would be negative, and that negative tells me that energy is going out. So it's just like in thermo, okay? So now the second part is what wavelength of light is required to make this transition. Well, now what I can do, I remember that E always equals hc over lambda. Okay, so I have a value for energy, even though this was delta En. I can still say all of that equals hc over lambda. So now to solve for the wavelength, I'm just going to do some algebra, because that's what it asked me for, what wavelength. So wavelength equals hc, now divided by E, so I just did some algebra. And we'll say that lambda is 6.626 times 10 minus 34 joules times seconds times 2.998 times 10 to the 8 meters per second, all divided by 1.936 times 10 to the minus 18 joules. And so let's do that. So on this one, I'm going to say times 1 negative to make that a positive. So we always use positive values. So like, you know, I'll put an absolute value sign around that energy. Because if I was doing this from 3 to 1, I would still get the same number, but it would be negative. I would just use the absolute value of that in my equation, okay? And so now I've got that in the calculator. I'm going to show you a handy trick what I can do. Because it's 1 over this number, right, 1 over the number I have in my calculator, I'm going to push that 1 over x button. Okay, great. And now I'm going to say that number times 6.626 E34 negative equals, and then now times 2.998 e to the 8 equals, and that, yep, that's a reasonable number. And I'll tell you why I know that's a reasonable number. 1.026 times 10 to the minus 7. And once again, let's do the units. Joules and joules cancel. Seconds and seconds cancel. So that's meters. And I know in 1 meter, there's 1 times 10 to the positive 9 nanometers. So minus 7 and positive 9 gives me positive 2. So that equals 1.026 times 10 to the 2 nanometers, which is the same as 102.6 nanometers, and that's ultraviolet. And that makes good sense that it's ultraviolet light, because if I back up here for a second, right, so all of these smaller levels, so the levels that are crunched together, are all giving me visible, right? So like 3 to 2 gave me red, and 4 to 2 gave me blue, and 5 to 2 gave me ultraviolet. So then it makes sense that 1 to 3 would also be ultraviolet, because that's a fairly large arrow in comparison to, let's say, the 3 to 2 or any of these other arrows, okay? So once again, the spacing between these energy levels, the higher they're spaced, the more energetic it is. And the more energetic it is, the more likely it's, you know, ultraviolet or X-ray or something like that, okay? Okay, so we're going to do more of these types of calculations in discussion.